Okay, good day students. We've just talked about properties of ionic compounds. What we want to do today is have a look at the formula units for ionic compounds. So the point of today is to really determine the formula of an ionic compound from the charges on the relative ions and name the compound. We'll need to just remember that the number of electrons lost gained is determined by the electron configuration of the atom. And we'll also note that transitional metals can form more than one ion today. Here we have a periodic table, and it's just showing us the valencies or the common ions formed by each element. So you'll notice that in group 1, for example, they all tend to lose one electron and get a charge of +1. Group 2 tend to lose 2 electrons and get a charge of +2 or a valency of +2. Group 13 tend to lose 3 electrons and get a valency of +4. Now the metals in group 14 tend to lose 4 electrons, so germanium and tin and lead tend to lose 4 electrons. Now group 15, so they become a charge of +4. Group 15 tend to want to gain enough electrons to get the nearest noble configuration of the noble gas. So they're going 1, 2, 3. They want to gain 3 electrons. So if they're gaining 3 negative particles, they're getting a valency or a charge of -3. Group 16 tend to gain 2 electrons to get the nearest noble gas configuration, and group 17 tend to gain 1 electron. There are a couple of interesting ones here. So metals generally lose their valence electrons and they become cations. Non-metals gain valence electrons and become anions. Now transition metals are these ones in the middle. So from here, these are our d block orbitals, and they form stable ions with incompletely filled d orbitals. And so we use Roman numerals to indicate the charge. So for example, if I were to form some iron chloride, you can see that there are 2 possible valencies for iron chloride. Now the 2 is the most common. So we would just write that as iron to chloride, and that indicates that the iron in this case has formed a valency, or an ion with a valency of +2. When we consider group 1 and 17, so that's our sodium lithium group, for example, with the halogens. So group 1 are alkali metals and group 17 are our halogens. You'll notice that group 1 has 1 valence electron, whereas group 17 are missing 1 valence electron. So what we should note then, the electron configuration is that we have 1 valence electron there, 7 valence electrons noted, and so the sodium atom will lose that electron to form that sodium ion. And so it's a positive charge, and it has a configuration of 2,8, whereas chlorine has gained that electron. So that's the electron that it's gained. It's got a charge, and it now has an electron configuration of 2,8. If I were to react group 1 elements, so the alkali metals, with group 16, you'll notice that group 16 elements only have 6 electrons on their valence shell, and so it's going to require a couple of extra electrons. So in this case, what we are describing then is the need for 2 lithium atoms. So we've got 2 of them over here, and we've written it in the formula down here. So we've got 2 lithium ions plus 1 oxygen ion, and we're producing lithium oxide. What else should we notice? That This 2 in particular describes that it needs 2 lithiums to balance out that 1 oxygen, and that's because lithium can only donate 1 electron at a time. You should also note that the charge for lithium oxide is neutral overall, and that should be the case for all ionic compounds. So if I were to react group 2 and 17, for example, so we've got magnesium. Now magnesium has 2 valence electrons, but group 17 only need 1 valence electron to fill their outer shell. So in this case, it's just a reverse of what we saw. We're just going to need 1 magnesium for every 2 chlorines. And so we describe that as magnesium plus 2 chlorines, and that will produce a magnesium ion and 2 chloride ions. And the end product is magnesium chloride, MgCl2. That describes 1 magnesium for 2 chlorine atoms. If we were to react group 2 and group 16, you'll notice that, for example, magnesium has 2 valence electrons, oxygen has 6 valence electrons. To get to the nearest octet, magnesium will lose 2, oxygen will gain 2, and so the nearest noble gas configuration for magnesium is 2,8, and it will therefore get a charge of positive 2. And the nearest noble gas configuration for oxygen is the same, 2,8, and it will have a configuration of 2,8, and it will form a -2 ion. So they combine at a 1-to-1 ratio. You can see that I have not put the subscripts down below magnesium or oxygen when the subscript is just 1. So when we write ionic formulas, there's a few methods that we can think of. First of all, just write the symbols and the charge of the 2 ions. Now I'm going to calculate the multiple of the 2 numbers in the charges. We can calculate how many positive ions are needed to equal the lowest common multiple, and calculate how many negative ions are needed to equal the lowest common multiple. We'll use the answers from the 2 previous steps to write the formula of the ionic compound using subscripts and the number of ions, and we will write the positive ion first. So if we're looking here at magnesium chloride, MgCl2, here's magnesium, it's in the second group, it will have a valency of +1. Chlorine has 7 electrons in the outer shell, group 17, it'll only need to gain 1. So we're going to just write it as 1 magnesium for every 2 chlorines to make magnesium chloride. We need to write the positive ion first, and that's the cation or the metal. So when we name ionic compounds, we name the cation involved first, and this is generally the metal name. And instead of saying magnesium chlorine, we'll say magnesium chloride. So we replace the ending or the suffix with IDE. And in this case, you can see aluminium oxide, and the formula is what? 2 aluminium and 3 oxygen. So that's aluminium oxide. Now sometimes when we work with ionic compounds, you'll notice that the ions can be monatomic. That means we're just using 1 atom. For example, if we are putting sodium with chlorine to make sodium chloride, we've got 2 single atoms or 2 single ions working together. But there may be a case where the ion is actually polyatomic, and ammonium is a good example. We don't have too many positive cations that are polyatomic, but ammonium here, NH4+, is a polyatomic ion. So a polyatomic ion are different groups of atoms in a set ratio. In this case, we've got 1 nitrogen and 4 hydrogen, and has an overall charge of just a positive. Now, we write the ratio the same way we would write an ionic compound with the subscript there, after each ion involved, so 1 nitrogen and 4 hydrogen, and then we put the charge as a superscript. So the ratio as a subscript, the charge as a superscript. Now, if we're looking at polyatomic ions, and particularly those involving oxygen, for example, you'll notice that the suffix or the ending will change. So if I look at sulfate and sulfite, so we have sulfate and sulfite. We've got SO3 2 minus and SO4 2 minus. So SO3 is sulfite. It has less oxygen than sulfate, which has SO4, 4 oxygen. So generally, polyatomic ions containing oxygen will end in ite or ate, and the ate for the ion with the more oxygen. Sometimes you'll also see polyatomic ions with hydrogen, and you would have heard of biphosphate. Another name for biphosphate is hydrogen phosphate. So sometimes we'll put in biphosphate instead of hydrogen phosphate. If you want to think about these visually, as I said before, ammonium is an important one. That's a positive ion, so a cation. Some of the other important ones that you'll come across is carbonate. CO3 2 minus, that's pretty popular. Hydrogen carbonate or bicarbonate, we'll see that occasionally. We'll see nitrates fairly often, which is NO3 minus. And then a sulfate are the ones that we tend to work with commonly. Occasionally for a 3 minus, we'll put in a phosphate as well, which is PO4 3 minus. What I'd like you to do now is pause the video and just see if you can name these compounds. So as we look down here, you'll need to note that what the metal is and what the non-metal is. So if I'm looking at the first one, we should see magnesium chloride. Then we could see sodium oxide. If I look at the third one, this is a polyatomic anion. So that's a little bit tricky, and that's a hydroxide. So that's this one here. So that's sodium hydroxide. The next one is potassium carbonate. Magnesium. Now this is an interesting one because we've got a 2 here after the brackets. So if I look here, it's a hydrogen phosphate. It's actually a dihydrogen phosphate. Have I got that there? I'll just lose it here. So it's got 2 hydrogen phosphates, so we can call that a dihydrogen phosphate. We've got a zinc nitrate. We've got a hydrogen sulfide, copper oxide. We've got lead chloride. Now this is an interesting one because we know that chlorine is just a single negative, so this lead must be a lead 4 chloride. Likewise, SN is tin, so that would be tin 4 chloride. And last of all, iron oxide. So we know that oxygen is -2. 3 times -2 is -6. And this means that 6 divided by 2, that's got to be a +3. So that's an iron 3 oxide at the bottom. So how did we go? So you can think about the symbols, the Roman numerals, particularly for the transition metals, or we can also think of them for the poor metals down the bottom right hand corner of the periodic table. When you've done that, are you happy that you can determine the formula of an ionic compound from the charges of the relative ions and name the compound? When you've done that, I've got a little bit of work for you to work through here.